Hello everyone, I'd like to welcome you to the spectroscopy course for the semester 2021. And this is, I think, one of those key courses that everyone kind of needs in their undergraduate education, particularly if you're going to further chemistry, but also if you're interested in other fields like, for example, biochemistry or biology. Having a knowledge of spectroscopy really is something that's, I think, quite important in the biological but also the chemical sciences. So that what we're going to be doing in this course is really doing a rather very brief survey of different types of spectroscopic methods that are used for structural elucidation in chemistry. We're going to focus most of our attention on the elucidation of organic compounds, with some excursions to maybe organometallic or inorganic compounds, but for the most part it will be restricted to organic compounds. And we're going to do this in a way where every week we look at a different spectroscopic method. So the starting point of this whole thing really is, what is spectroscopy? What do we mean by spectroscopy? Well, as the spectro comes from the electromagnetic spectrum. So we're somehow using the electromagnetic spectrum in spectroscopy, and we are using it to perform structural elucidation, to try and understand what the structure of a molecule is. It doesn't have to necessarily even be a well-defined molecule. It can also be something like a surface. You have certain spectroscopic techniques that elucidate the surface of solids. You can look at macromolecule structure elucidation, and so on and so forth. But we are using the electromagnetic spectrum, and we are using some instrumentation and seeing how certain parts of the electromagnetic spectrum interact with a molecule or a molecular entity or a solid, the chemical species that's under investigation. And using this interaction, if you will, between the electromagnetic spectrum and the molecule, you can glean some information that helps you understand what the three-dimensional structure of the molecule is. And if we see here, just to remind you from basic physics, we have the electromagnetic spectrum. We have, of course, on the one end, the gamma radiation, extremely short wavelengths, right? Extremely short wavelengths with very high associated frequencies. To the other extreme on the left here, where we have radio waves with very long wavelengths, right, in the order of 1,000 meters or even more. The radius or the diameter of the Earth even, wavelengths of that magnitude, and kind of everything in between: microwave radiation, infrared, visible, ultraviolet, and X-ray radiation. And of course, there's this relationship, as you might recall from physics, which comes up again and again in spectroscopy, the famous wave equation, E equals hc over lambda. This relationship between c, which is the speed of light, which is the speed of electromagnetic radiation, and lambda, which is the wavelength, and the associated energy of that, where h is Planck's constant. So maybe we should just write that down, because this is something you're going to see again. Energy of electromagnetic wave is h, Planck's constant, c over lambda, the wavelength. There's another important wave equation, which is also very important, and that is, of course, the relationship between the speed of the wave, the speed and the frequency. So that's also important. So these two equations are very important: equals hc over lambda, and then, of course, the relationship between frequency and wavelength. Now, you'll notice in the middle of this electromagnetic spectrum is visible radiation. That's kind of what we can see. You can see here in this thing at the bottom here, sort of the colors, if you will. And so that's what human eyes can see. And it's quite interesting to note that that's really right smack bang in the middle of this spectrum. Okay, this range of wavelengths. What you see at the bottom here are names of different types of spectroscopies and sort of the frequency range at which they're employed. So sort of at the upper end, you have something called Mössbauer spectroscopy, which relies on nuclear excitations, okay, which therefore requires gamma radiation. And Mössbauer spectroscopy is actually something that you can use to determine the structure of molecules that contain iron or tin and some other elements. It's not something we're going to discuss in this course, but just by way of introduction, Mössbauer spectroscopy relies on nuclear excitations, right, driven by absorption of gamma radiation, and somehow that gives us information which we can then use to do structure determination. Sort of moving a bit down to slightly longer wavelengths, we have at the X-ray region of the electromagnetic spectrum, you have certain types of X-ray spectroscopy techniques that exist, which also give you information. And here I've got an example, XAFs, which is a type of X-ray spectroscopy. Moving a bit down, sort of to the ultraviolet visible region, sort of where these two kind of overlap, UV-Vis, we have ultraviolet visible spectroscopy, which is something we're going to discuss shortly. And then we move to infrared, the infrared region of the electromagnetic spectrum. We have IR spectroscopy. We have EPR spectroscopy, which is something that involves elucidating the structures, if you will, of radicals, species that have unpaired electrons. Typically for this, you need microwave radiation. And then finally, at the end, you have NMR, very important NMR, one of the most important techniques, certainly in organic chemistry, for structure elucidation, something we're going to spend a lot of time discussing in this course, around 10 to the 3, you know, with a wavelength of approximately 1,000 meters or more, depending. So, yes, these are very, very limited examples, but it's just to show you that the field of spectroscopy really spans the whole electromagnetic spectrum. Now, there's a further technique that we're going to discuss in this course, which is mass spec, mass spectrometry. That's not really, formally speaking, spectroscopy, because a spectroscopic method typically involves the interaction of electromagnetic radiation with a sample in a specific instrument from which we then get information. But it will, it's an important technique nevertheless to determine structure, which involves, for example, bombarding molecules with a high energy beam of electrons, for example. So we include that in the course because it's important in terms of structure elucidation. So what this course really is all about is it's really an introduction to spectroscopy. Right, and the purpose of this course is actually to give students the tools to be able to, when confronted with infrared, nuclear magnetic resonance, mass spec data, etc., you know, propose a structure of a molecule, so structure elucidation. It's a rather practical course, okay? It's taught in a practical way. In other words, I'm not teaching this from a very theoretical perspective. You have spectroscopy courses that are very heavily laden with quantum mechanics, and that's not the case in this course. So this is a sort of a very, let's say, simple and accessible spectroscopy course where the emphasis is on trying to interpret a spectrum more than the theory. We will discuss the theory of each technique, but only superficially. The formal theoretical background of many of these spectroscopic methods is sufficiently sophisticated, even for graduate level courses. So I keep things simple and try to get to the analysis of spectra as fast as possible. And finally, then, of course, you know, also looking at instrumentation challenges and issues. So we're going to look at the theory, the basics. We're going to look at instrumentation. We're going to look at how the techniques work, but the key emphasis is trying to solve and elucidate structure. And so the first technique we're going to discuss is UV-Vis, ultraviolet visible spectroscopy, right? This is a very useful tool. It's a classic. And if we come back to our electromagnetic spectrum that I showed you a moment ago, we sort of smack bang in the middle of it, you know, going from the one side gamma rays. I mean, you can even go higher to cosmic rays, which have an even higher frequency. But we're sort of right in the middle in terms of wavelength and energy, frequency, should I say. And ultraviolet visible radiation is actually sort of at the cusp of visible and ultraviolet light, okay, as you can see depicted here. And we're going to use this wavelength to actually, or this range of wavelengths to get electronic information, in this case, of a specific molecule. So what we're going to look at is we're going to look at the phenomenon of colors. What gives something color? We're going to look at some physical considerations, instrumentation. We're going to look at the experimental parameters, nomenclature, some names and concepts. And particularly, we're going to focus on the effects of conjugation in organic chemistry, right? And finally, we're going to look at some functional groups and sort of a practical guide at the end. So what gives something color? Well, as most of you probably know, the color that is emitted from an object is kind of the inverse to what is absorbed, right? And so you basically have to, if you see something that's orange, it doesn't mean it absorbs in the orange region of visible light. It means it absorbs in the reciprocal region, maybe something like blue, right? And that absorption has something to do, it doesn't just absorb haphazardly, it is quantized. And it absorbs a specific wavelength due to the chemical structure and due to the specific energy requirements for electrons to be promoted to a higher energy level. And that's the cornerstone of UV-Vis spectroscopy. We're kind of quantifying this. So if we take the example of beta carotene, which is what gives carrots their beautiful orange color, if you record a UV-Vis spectrum of this, you see a strong absorption at about 452 nanometers, which we denote lambda subscript max, you see depicted here. And 452 nanometers is in the blue region of the electromagnetic spectrum, in the visible region, okay? And obviously, if it absorbs here, it's going to transmit light that is orange. That's why we see orange, because it absorbs blue. Now, this 452 and the specific absorption, you can see beautifully in a spectrum, is not just something that happens haphazardly. It depends on the chemical structure. You see here, beta carotene is highly conjugated. You see all these double bonds here. That, of course, gives it, we call that a chromophore, which means it's a collection of atoms that give molecules color through absorption, essentially. But what's actually happening here in a very simplistic way is we're actually exciting electrons from the ground state into an excited state, okay? And this is typically the case with many spectroscopies, but also with UV-Vis. In UV-Vis, we're essentially exciting electrons from a ground state into an excited state, okay? And this energy gap here, right, is going to be dependent on the chemical structure. And the chemical structure and the way the atoms are bonded together is going to affect this energy gap. And as we saw, E equals hc over lambda, that specific quantized energy gap, right, it's quantized, meaning it can only absorb one specific value, that is going to correspond to a specific wavelength according to hc over lambda, where lambda is the wavelength. And so this is a relationship between energy and wavelength absorption. It's going to absorb at a specific wavelength, and that's when you're going to get a spectrum. Now, in the case of UV-Vis, right, we see on the left here, we've got different types of molecular orbitals, right? So you've got to think about this in terms of molecular orbital theory. And basically, molecular orbitals are just the, really, if you look at molecular orbitals in a molecule, it's where the electrons are sitting from a molecular perspective. And of course, any molecule has these types of molecular orbitals. You've got sigma molecular orbitals, pi molecular orbitals, n-type molecular orbitals, and then anti-bonding molecular orbitals, sigma star and pi star. And so what you're seeing in UV-Vis actually very often in a spectrum is transitions essentially from basically down here to up here, okay? From the occupied levels downstairs, n, pi, and sigma, to the unoccupied levels, sigma star and pi star. And so you can, for example, have an n to sigma star transition, right? You can have an n to pi star transition. You can have a sigma to pi star transition. You can have a sigma to sigma star transition. And you can have, in fact, one of the most typical ones is pi to pi star. So of all of these transitions, pi to pi star transitions are typically very visible, and they tend to give very large absorptions, okay? So, but you can also have these other absorptions. And of course, each of these lines here, what happens is an electron will absorb a specific amounts of energy from a specific, from the electromagnetic spectrum, be promoted into a higher energy level, and that will correspond then to an absorption. And then you get an absorption spectrum, okay? And that will tell you something about the energy levels, right? It tells us something about the energy levels and the types of electronic transitions that are taking place. This is an example of a spectrum, a sort of a UV-Vis spectrum for sodium. You can see here four lines in the spectrum. This is actually not really UV-Vis, but because this is just elemental sodium. But this corresponds to the specific quantized energy levels within sodium. So here you've got to look, actually, this is actually very simple. It's even simpler than the slide I showed you before, which is looking at it for a whole molecule. Here we are looking at the possible electron transitions within a sodium atom between different energy levels, right? The first shell, the second shell, you know, and what possible energy levels there are. Electrons can, for example, be promoted from the first energy level to the second energy level and fall back down, you know, in a process of relaxation. But anyway, so what you see are very sharp lines in the spectrum corresponding actually to these electronic transitions within a sodium atom. Okay, so this is not UV-Vis, this is kind of just a spectrum of sodium, but the principle is similar. Now, what you have in spectroscopy very often is you have essentially three modes of, let's call it, say, movement. You have translational motion, you have vibrational motion, and you have rotational motion, okay? Molecules do all three of those things: translation, rotation, and vibration. And very often what you see also with something like infrared spectroscopy and other types of electronic spectra is that you have sort of a combination of these different types of motion, let's say. So you can, for example, have vibration and rotation superimposed on electronic transitions. So you have electronic transitions, and then you have translation and vibration, okay? And those translation and vibration and rotation energy modes are also quantized, as are electronic transitions. And sometimes you have sort of an interaction, if you will, of these different types of quantized energy absorption. And you see that in the spectrum, okay? So when you have something like infrared spectroscopy, which we'll discuss in a moment, you can actually record rotational infrared spectra, which looks at rotational absorptions, molecules rotating, okay? So you can do rotational spectroscopy, but what we're concerned with here for the most part is just, in this context, is just electronic transitions. So here is the spectrum of beta carotene. This is an experimental spectrum. You'll see it absorbs at around, it has a lambda max value here around 4 50, if I look at the spectrum. So the apex of this absorption peak we call lambda max. I'll maybe just write that down. Lambda subscript max, max standing for maximum. And you'll see it quite clearly absorbs in the blue parts of the electromagnetic spectrum, or in the blue part of the visible spectrum. And that means that the color is going to be the reciprocal of that. We look at the color wheel, and it's going to be orange. That's why it appears orange, okay? And so this is the major transition in this molecule, okay? Now, the way to understand all of this stuff is by the very important and critical Beer-Lambert law, okay? The Beer-Lambert law is a relationship between absorbance, right? What the molecules, what proportion of the incoming radiation is being absorbed by the molecules by these transitions, and what proportion is being, let's say, transmitted. And the relationship is actually depicted here. The absorbance equals epsilon LC. Epsilon is something we call the molar extinction coefficient, or we also call it molar absorptivity. And that is actually a measure of how absorbent a molecule is. Of course, the higher the molar absorptivity, the higher will be the absorbance, right? Because you can see that mathematically, the higher epsilon, the higher is A. And L is just the path length of the cell. Obviously, the longer the cell, the more absorption there's going to be, right? And C is the concentration, the molar concentration. The higher the concentration means that there's going to be more of the molecules present, and you're going to have a higher absorption. Now, so the simple way of understanding the Beer-Lambert law is just that A, absorbance equals epsilon LC. But you can think of absorption in terms of this logarithmic relationship, right, base 10, which is really absorption is essentially nothing more than the proportion or the ratio of incoming radiation, I subscript O, versus, let's say, the radiation that manages to pass through expressed in a logarithmic fashion, okay? So in fact, you know, this I is just intensity. This is intensity of light entering and leaving the cell. So IO is intensity of light, or let's say radiation, to be more rigorous. The intensity of light entering is I0, and the intensity of light leaving is just I. And the ratio of those two is then absorption, which is then equal to epsilon CL. You can actually find epsilon, of course, experimentally by running a series of experiments where you vary the concentration, look at the change in absorption, and you can actually then determine the molar absorptivity or extinction coefficient at a specific wavelength for a compound. And that's maybe something we can look at when we meet up. So here is another organic compound, isoprene. And this is just what you kind of get from a UV-Vis spectrum, is you scan the entire series and you get an absorption. Sometimes you don't get an absorption. There's molecules that don't absorb at all, right? For example, alkanes. If you take something like methane or pentane and you run a UV-Vis spectrum, you're not going to see much, right? So you need a chromophore, which is a group of atoms that absorb, right? And here you've got these conjugated double bonds here. Those guys are going to enable this absorption to take place. You get this beautiful absorption here at 220, which is actually at quite a low wavelength. How does this work from an experimental or instrumentational perspective as shown here? It's actually quite straightforward. You essentially have a lamp, right, which emits radiation, which goes through a monochromator, right? This is actually just something to kind of get the wavelengths in a monochromatic way. You have a deuterium lamp and you have a tungsten lamp, right? Deuterium lamp sort of emits radiation from 180 to 370 nanometers, and tungsten goes from 350 to 2500. And those two kind of shine through the monochromator together, and via a series of mirrors, you can see here, passes through a series of mirrors, and you have S, which is the sample, and R, which is the sample, and S, which is the standard, right? So in other words, you have just the solvent, because you have to record this in a solvent, and then you have your compound there, and then essentially, the instrument determines what ratio of the incident radiation is going through, and what ratio of the radiation is actually being absorbed, and it's processed by a computer, and you get a spectrum like we just saw moments ago, right? So essentially what it does is it passes through a monochromator, you scan wavelengths, you'll typically start at a high value, 2500, and it will scan to lower and lower values, and while it's doing the scan, right, you can actually then see if there's an absorption or not at a specific wavelength, right? So it's actually quite a straightforward technique. We have these facilities, as some of you might know, right? You have different types of instruments. This instrument on the left here is actually one of the more sophisticated ones that we have available, right? This one over here is actually something that you typically see more in an undergraduate teaching lab, right, where you actually sort of get a printout on a computer screen here that's built into the instrument. This one is actually connected to a computer screen, or to a computer program that you can actually do more higher order analyses, okay? And this is actually what the sample cell looks like. Notice that there's two places to install a cuvette. That's the name of the thing that you put in there. The one is for the solvent, just the solvent, the standard, and the other one is for the solvent with the compound in it that you're analyzing. And then, of course, as you see in this picture here, essentially you're looking at the standard and you're looking at the sample simultaneously, and from that you're getting a spectrum. These cuvettes that are used, this is again looking at some technical issues. The best ones to use are made of quartz. They tend to be very expensive. You have to use quartz because it's highly transparent, okay? If you use normal glass, you're going to get, some absorption in the UV side of the electromagnetic spectrum. That's why quartz is used. You can, however, use glass and even plastic cuvettes, with limited utility, but the spectra tend not to be of such high quality. But that's perfectly acceptable for, let's say, an undergraduate teaching lab. But if you want to publish something, let's say, it's better to do it in quartz, so you can really make sure that you're not getting any absorption, that you don't want. As I've said, you have to record these spectra in solvents. Of course, there's a range of solvents that you can use. I mean, here I've just got a few examples. The problem is the solvents themselves actually might have absorption, okay? And you've got to be careful of that. And so that's the first thing. Do the solvents have their own absorption, which might mask an absorption of the molecule? And the second, and that's an important thing, and the second thing you have to consider is cutoff, right? So you have so-called solvent cutoff for different solvents have a characteristic cutoff region, okay? And yeah, so you can see, for example, the solvent cutoff for acetonitrile is 190 nanometers. So if your compound, for example, let's for argument's sake, as an absorption below that, then of course you shouldn't use acetonitrile, okay? So these are important things to be aware of. And just to show you how the solvent can actually affect the UV-Vis spectrum, I have an example here actually of how it can change the so-called fine structure of a UV-Vis spectrum. In other words, looking really at let's say the resolution, if you will, in different solvents. And you can see here, if you record this specific compound in ethanol, you get roughly the same, But if you do it in isooctane, you can see that it has a much higher, let's say, a more well-resolved structure where you can see specific absorption peaks, 3 or actually 4, in fact, right? Whereas in the ethanol, you'd say, okay, well, there's only 1 or 2 with a shoulder. So the use of the solvents is very important. And the reason for this is also that you have the solvent also interacts, of course, with the molecule that you're studying. And so, you know, you might have phenomena like hydrogen bonding taking place. So you've got to be very careful with the solvent that you're using in UV-Vis. Again, you can see that clearly here. If you run, if your solvent is isooctane, you're getting a nice, clean, beautiful, highly resolved UV-Vis spectrum. You take the compound and you dissolve it in ethanol, and you kind of lose that resolution. That's interesting. You can learn something there. In this case, you can learn that there's hydrogen bonding going on, for example. But still, you've got to be careful that you select the right solvents. And solvents can also, in fact, affect the position of the absorption. So here you can actually see we have we have a specific analyte that we're analyzing, and we've analyzed it in various different solvents: dichloromethane, chloroform, you know, acetonitrile, THF, methanol, and so on, DMF, dimethylformamide, and so on. And you can see clearly in the spectrum, you have more or less the same form of the spectrum in roughly the same region. You have sort of between, let's say, 420 and 470 is the region of absorption, but you can see that shifting left and right. You've got more or less the same number of absorption peaks in the spectrum, but the actual value is shifting, okay? So that's why when you record a UV-Vis spectrum, you always have to indicate the solvent that you're using, because the solvent most certainly affects the position of the absorption. And so the solvents is important, right? That's going to affect the spectrum. It's going to affect the position of the absorption peak. Sorry, the internet crashed there for a moment, so I'm back. So what I was saying was the important thing is also that the concentration is very important. Okay, so we've seen that the solvent affects the relative shift of the band positions, but so does concentration. And this is obvious from the Beer-Lambert law. The higher the concentration, the higher the absorption. You see on the y-axis we have absorption. Obviously, lowering the concentration lowers the absorption. And typically, if you record a UV-Vis spectrum, and you can see a beautiful example here, you do it at many different concentrations, right, so that you get this nice progression of signals that you see here, going from, let's say, concentration in this case of some analyte at 160 all the way down, and you can see how this affects the absorption. And if you were then to actually take that data and plot it, you could actually determine the extinction coefficients at this specific wavelength, lambda. So concentration affects the nature of the spectrum. Now let's talk about some important UV-Vis nomenclature. We have the notion of a chromophore, which I've alluded to before. It's a collection of atoms that produce an absorption, quite simply. The fancy name is chromophore. Chromo means color, right? In other words, if it produces an absorption, then that means it's going to emit a specific wavelength of light, of visible light, and give it a specific color. That's why chromophore, okay? Now you can have the notion of a bathochromic shift, which is really a shift to lower energy or longer wavelength. It's also called a red shift. Hypsochromic shift, which is the opposite of that. That's a blue shift to higher energy or shorter wavelength. Remember this relationship between energy and wavelength. And then a hyperchromic effect, which is an increase in intensity, and a hypochromic effect, which is a decrease in intensity. Okay, so these are kind of 5 important terms that one needs to be aware of in UV-Vis, specifically bathochromic and hypsochromic, right? Because if you're discussing, let's say, a series of compounds that are somehow related in a chemical family, and you want to discuss sort of, let's say, the progression of the data, then very often you'll see by, let's say, tweaking functional groups and stuff like that, that you'll have a red shift or a blue shift. And that tells you something very important about how, by changing the structure of the compound, you're changing these energies and therefore the position of the absorption. So this is just a summary of what I've just said. Bathochromic is red shifted. Hypsochromic is blue shifted, right? Remember, blue shifted means lower wavelengths. Red shifted means longer wavelengths. The way I remember that is red is infrared, that's long waves. Blue is close to ultraviolet, that's short waves, right? And then you have hyper and hypochromic, which is really just the intensity. So very simply, for example, if you lower the concentration, right, then you induce a hyperchromic effect, right, because then the absorption is lower. So this is very important. Now, the next thing I want to discuss, specifically with reference to organic chemistry, is the effects of conjugation. Now, you all know, you've learned about conjugation in organic chemistry. Conjugation is really the effect when we have successive, let's say, multiple bonds that are somehow separated by short distances. You have this notion of conjugation, which often leads to stabilization and other interesting properties. And you can see that also in UV-Vis spectra. Okay, so here, for example, I have a simple alkene, right? A simple alkene, and what I've actually got depicted here is really the pi and pi star orbital, okay, of this alkene. So you've got the bonding pi and you've got the anti-bonding orbital at the top here. So I've called this phi 2, but this is in effect the molecular orbital pi bond, which is occupied with 2 electrons, and this is what we call the pi star orbital. And these typically make up good chromophores and are quite absorbent, okay? They're quite absorbent, and so you see these very nicely in a UV-Vis spectrum. Now, if you conjugate this, so here I've got now a series of these things, right? If we compare, for example, ethylene and 1,3-butadiene, right? 1,3-butadiene is a conjugated diene. What actually happens there is that if you look at these energy levels, this pi to pi star transition, it actually goes down in energy, right? So these are pi to pi star transitions, and the higher the conjugation, the smaller the energy difference between the pi and the pi star orbital, okay? And if I have, for example, if I've put on another double bond, right, and I conjugate it further, that pi to pi star transition is going to get even smaller, right? So this is a very interesting effect where you can actually elucidate the degree, if you will, of the degree of conjugation in UV-Vis spectra, okay, for organic compounds in a homologous series of them. And, you know, this has got something to do with molecular orbital theory and stabilization, okay? You kind of see that depicted here, right? So what we have shown here for butadiene is we've basically got 2 pi-type orbitals, right? And we've got 2 pi star orbitals, right? These are pi star orbitals here, whereas in the case of ethylene, we just have 1 pi and 1 pi star orbital. And you can actually see from the phasing of these lobes what these orbitals, these molecular orbitals, actually look like. And if we play the game further, actually, very interestingly, if you go to hexatriene and octatetraene, you can see that the energies get smaller and smaller and smaller. And notice also that, of course, if you have, each time I add on an extra pi bond, I'm adding on an extra pair of pi and pi star orbitals. That's kind of makes sense, right? Because each pi bond needs a pi orbital and a corresponding anti-bonding pi star orbital. So that's why for ethylene, I've just got 1 pi and 1 pi star, butadiene 2 pi pi star orbitals, and so on and so forth. But the energy transition that you're going to see is this one in the middle here, from the last pi to the first pi star molecular orbital. And that energy level gets smaller and smaller as the length of the conjugation increases. And that's an interesting effect. And here you can actually see this effect. So here I've actually got the conjugated, these are the experimental UV-Vis spectra, right, absorbance to wavelength, for the triene for n equals 3, n equals 4, and n equals 5, okay? And that's just the number of double bonds. So we're looking at basically this guy, and the next one in the series, okay? And you can actually see that you have this beautiful shift as evidenced by the reduction in this pi to pi star energy gap, right, as a result of increased conjugation. So this is just another example of a nice compound that has a beautiful color, right? I don't think I'm really going to discuss that. That kind of more or less brings us more or less to the end of the lecture. We've looked now at a brief overview of UV-Vis instrumentation, what it means, what it corresponds to. But you can use UV-Vis spectroscopy with some utility, although it's limited in structure elucidation. So if I give you a sample and I say, what is this? And you record a UV-Vis spectrum, you're not going to learn much other than the electronic transitions that are taking place. If you know a priori what the structure of the compound is, and you then record a UV-Vis spectrum, it's very interesting to understand the electronic structure of that compound, and it's useful in understanding the electronic structure of that compound. But if you don't know the structure and you record a UV-Vis spectrum and you have no idea what it is, it's going to be very difficult for you to actually figure out what the compound is, if not impossible. So UV-Vis spectroscopy, unlike NMR, which really sort of gives you an in-your-face version of what this thing is that you're analyzing, is something that tells you about the electronic structure, it tells you about electronic transitions, it tells you something about, let's say, the molecular orbitals maybe, it tells you, you know, you can figure out what sort of transitions are taking place, and it's very valuable, but it has limited utility in actual structural elucidation. However, it can actually be used to you know, give some hints as to what class of organic compound you're dealing with, if you know it's an organic compound. So, for example, alkanes, alcohols, ethers, and all these other functional groups do have some characteristics in the UV-Vis spectrum that you may be useful in your overall, let's say, suite of characterization techniques when you are doing structural elucidation, okay? And I think that's important to know, and just sort of as a practical guide, but you'll see that this is not very rigorous. It's just something that you can use as a confirmation if you have all the other spectra in place. If you have a band of low medium intensity above 220, it might correspond to an alcohol, ether, cyano groups, amines, for example. If it's between 250 and 360, a simple unconjugated chromophore. If you've got two bands of medium intensity, then it might point to an aromatic structure, right? If you've got a band of high intensity above 210, it's probably a diene, an unsaturated ketone, or a polyene. We just saw an example of that now when we looked at that series of conjugated systems. And if you've got two bands of low intensity, right, above 300 and another one below 250, it denotes a ketone, an acid, an ester, or an amide. So this is actually quite useful. I mean, maybe I was a little bit unfair to this technique a moment ago. It is useful, and you can use it in combination with other spectroscopic methods to say, to hint at what sort of functional groups are present if you use the simple guide. But of course, it's not going to tell you much more beyond that, okay? But it's important in the overall grander scheme of things. From a personal point of view, as somebody who's a researcher, I use UV-Vis spectroscopy at the end. If I know what the chemical structure is, I know what it looks like, I will then record a UV-Vis spectrum as a final characterization point, right, which will usually correspond to 1 or 2 or 3 values or whatever, and that will tell me something about the energy levels in the molecule chromophores and so on. One of those will typically correspond to a color, let's say. Okay, so it's important to do this, but it's also important to realize that its utility can be quite limited. So the important take-home message from this lecture, which sort of things you have to know, the Beer-Lambert law and how to manipulate it. You might have questions where you have to find the concentration for a specific absorbance, or find the ratio of incident versus transmitted radiation, etc. Right, you need to really understand what a typical UV-Vis spectrum looks like, instrumentation, these important terms that we learned about, conjugation effects, and be able to use decide what sample you need to use for your specific sample. So that's the formal lecture on UV-Vis. We'll have an opportunity to unpack this a little bit more in the flip session, where I want us to have a look at some examples of UV-Vis spectra in practice, and also look at actually how one would plot this data to find epsilon. So we'll unpack these terms a little bit more, these things a bit more, and look at it in more detail in the lecture. Okay.